All right, one more time. Everybody hear me loud and clear in the back? Good. All right. So welcome everybody. This is our first lecture of the semester. Very happy to have you all here. I'm Ben. I'm the outreach coordinator for the Cornell Astronomical Society. If you don't know who we are, we'll talk about that at the end. Right now, I'd like to just give a brief introduction. So this is Professor Cordes. He's the George Feldstein Professor of Astronomy right here at Cornell. It's wonderful. He leads a research group specializing in radio astronomy. And they specialize on some things to pulsars, to fast radio bursts, which is very interesting and very foreign to someone like me. He's also an expert in signal processing, astronomical modeling, and statistical interference inference. My bad, guys, sorry. And his work has spanned the cosmos. Thank you. So tonight we're going to celebrate the pale blue dot image, which was taken 34 years ago on Wednesday, by having Professor Cordes talk about Voyager and talk about the data that Voyager is still sending back to us, even roughly 10 years after it left the solar system. And he's also going to talk about other, other data we're gleaming from the interstellar medium and things way beyond where Voyager is right now. So please join me in welcoming Professor Cordes, and I hope you enjoy the lecture.
All right. Thank you, Ben, and thanks for the invitation to speak. As you can see, I'm going to talk a bit about Voyager, but I have to tell you, I am not a planetary scientist. For me, the solar system is too close, generally. Uh, but given that the Voyager spacecraft have left the solar system, for me, that now makes them interesting. I'm being a little facetious because the Voyager spacecraft have been fantastic ever since they were launched in 1977. And I can also say that my career has sort of paralleled Voyager because I was a postdoc when they were launched. And I came to Cornell in 1979, saw a lot of the great results from Voyager, both spacecraft, as they did the exploration of the solar system. And then in 2019, my group started looking at Voyager data after the spacecraft had left the solar system, because we were interested in the so-called interstellar medium. And anyway, that's the gist of what I'm going to be talking about. So I'm not going to really talk much about the solar system per se, but the nearby neighborhood of the solar system. Okay, so the team that has worked on the result that I am going to talk to you about, Stella Acker got her PhD last May. She worked for 3 years on Voyager data, and I'll be talking about that. So she's currently a postdoc at Caltech and the Carnegie Observatory. She's a Brinson Fellow. My other long-term collaborator is Shami Chatterjee. He's on the research faculty in the astronomy department. And then there's a graduate student, Sashni Balsky, who has just submitted a proposal to NASA to continue some of this work. But I did want to say, though, that just going back to the beginning of the Voyager project, well before launch, there was Cornell leadership by a number of faculty members, including Carl Sagan and certainly others. And so they helped design the mission, did a lot of the important science for the mission, as it went through the solar system. And then there's some really interesting public outreach aspects of this. I think you all know about the pale blue dot, right? Yes? And you know about the gold record? Yes. Okay. So here's the basic setup. You had both spacecraft launching in the second half of 1977, and they did this grand tour of the solar system on these different trajectories. And then they went on their way to the interstellar medium. So here's the gold record, there's one on each of the spacecraft. So many of you said you know about the gold record, but I wanted to say a few things about it. So this is the cover of the record, and the record itself contains images, music, sounds, greetings in different languages. But on the cover, these engravings have some astronomical meaning. But first of all, the cover tells you how to play the record. So if there is any advanced civilization that somehow picks up Voyager, and they get their hands on this record. You know, there's some instructions here about how to play it. There's a depiction of a hydrogen atom here. And then here, these spoke-like things represent, first of all, the solar system is at the center here, and these are the directions to a few nearby pulsars. And encoded, well, the length of these vectors represents the distances to the pulsars. And then encoded along here, you can't really see it, is a digital representation of the spin period of each pulsar. So the idea behind this is that if this is ever picked up by another civilization, let's say 100,000 years from now or something, they will be able to backtrack because the pulsar periods get longer with time. And so they can trace back and determine when the launch, when the launch took place and from where. So that's kind of an interesting feature of this. Okay, so here's the spacecraft itself. The biggest piece of it is this reflector, 3.7 meters. And as it turns out, that's almost exactly the same size as the reflector we have on the top of Space Sciences that we use for a lab course in radio astronomy. There are a number of instruments here. Let's see, one measures cosmic rays. There's a magnetometer that measures magnetic fields, so the spacecraft are measuring these things in situ, as it propagates through either the solar plasma or the interstellar plasma. Okay, so there's some other instruments here. The one that is important to us is the plasma instrument, and there's some antennas that come off here that are part of the plasma experiment. I also wanted to point out that this is powered by a radioisotope thermoelectric generator. So at launch, there was 470 watts provided by these generators to drive all these instruments. The half-life of plutonium is 88 years, so the power supply is waning. And it's a little bit more severe than that right now. So it may be that Voyager 1 is no longer functioning. It's functioning, but it's not sending data back as of just a few months ago. But people are trying to fix it. Okay, so here you can see the trajectories. So this part of this diagram is looking down on the solar system. And this is the trajectory of Voyager 1 with the year marked here. And then this is Voyager 2. This part of the diagram is looking from the side. So one of them, they were both launched to go out of the ecliptic plane, so out of the plane of the solar system. And you can see the year markings here. So an important milestone for Voyager 1 was it crossed the heliopause in 2012 and 2018 for Voyager 2. So if I say heliopause, how many of you know what I mean by that? Okay, some wavering hands, yeah. Anyway, you'll know more by the time I finish. Okay, so here's another view of the instruments and so forth. I guess there's no real additional information here, but the planetary radio astronomy and plasma wave antenna, that's of importance to our group for the data, and I'll show you some of that. So let's see, this is, I don't know how well you can see this, but this shows the overall timeline, 1977, flybys of Jupiter and Saturn by both Voyagers. Voyager 2 went past Uranus and Neptune, and that was it for the planets. Carl Sagan arranged in, so that February 14th, Valentine's Day of 1990, he and a group of people arranged for the camera to look back at the planets and take pictures of the planets. So that was a pretty big deal. And then, well, it says here that Voyager 1 passed the Pioneer 10 spacecraft, which was launched, I don't know, something like 8 years before that. So the Voyagers were going quite fast. And then there are a couple of features here. The Voyagers crossed what's called the termination shock. So it was 2004 for Voyager 1 and later for Voyager 2. And then they entered interstellar space. So what does entering interstellar space means? It means crossing the heliopause. What the heliopause is, you may be able to see in this diagram. So we have the solar wind emanating from the sun. It's moving quite fast, like 500 kilometers per second, typically. And if there's a big flare on the sun, then you get a blast of particles and waves going even faster. But anyway, that wind coming off the sun plows into the interstellar medium at some position. And where there is pressure balance between the solar wind and the interstellar medium is the heliopause. Okay, so there is a distinct boundary. It's a physical boundary, and it's a good definition of inside or outside the solar system. Okay, so anyway, that's what we mean by entering interstellar space, but it's a little more involved than just that as well. So here's the family portrait, February 14th, 1990. Here are the images of 6 of the 8 planets. I don't include Pluto these days. Mars and Mercury were not in favorable positions to be imaged at this time. But anyway, you did see the grand tour. And the most important of these, I think, historically, is the image of Earth so this little dot here emits the zodiacal dust light. And then there's the famous quote from Carl Sagan, where he beseeches us to be more humble as a species, I would say. He uses fancier language than that. He says there is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. So that was vintage Carl. Okay, so how did we know then that the Voyager spacecraft left the solar system? People knew approximately where this boundary should be because, there were various kinds of measurements and the physical models that I talked about of pressure balance, a pretty simple concept. So there were estimates, but they were wrong because a lot of this depends on details. So the first evidence was from the cosmic ray. So anyway, here's the heliopause definition. And as it says here, prior to Voyager 1, the heliopause location was unknown in any kind of precise way. But the first clues about the crossing of the heliopause came from the cosmic ray instrument. So this is an interesting part of the story because the sun gives off cosmic rays. Cosmic rays are highly energetic particles that can do damage to living things. So there's some danger to them. So the sun gives them off, but also there are cosmic rays that come from outside the solar system. Basically, they come from particles that surf. They surf. What do they surf? They surf the shock waves from supernova explosions. And so those particles get accelerated and they're coming at us from all directions in the galaxy. So anyway, what happens is that the solar wind shields us to a large extent from the interstellar cosmic rays, but we still have the cosmic rays coming from the sun. So at this boundary, at this time here, which is roughly mid-2012, you can see up here that the galactic cosmic ray count rate went way up like this. It's just almost like a step function. And then at the same time, the solar cosmic rays went way down because they don't make it out as well through the heliopause. So this is a fairly sharp transition here. And so anyway, that was sort of a textbook demonstration of crossing the heliopause. Okay, so then there's another instrument, the plasma instrument. So it makes use of these basically just long wires, these antennas that have been dangling off the spacecraft for the last not quite 50 years and sending back data. So anyway, with that instrument, what it measures is the actual density of the gas that Voyager is plowing through. And it's quite low density, but anyway, we're talking about the plasma density, the number of particles per cubic centimeter. Typically, the interstellar plasma density is about 100 times bigger than it is in the solar wind. And so what you actually saw was this big jump in the density. So the kind of density I'm talking about here, this is, again, is in particles per cubic centimeter. So the big jump went from 1,000th of a particle per square centimeter to 0.1, factor of 100. So that's a big effect, but we're still talking about almost a perfect vacuum by laboratory standards. I mean, that would be a superb vacuum in the lab, but it's, interstellar space is not really a vacuum. So anyway, this also, this happened at the same time. So again, when I think I didn't point it out, but it was when the spacecraft was about 120 astronomical units from the sun. Okay. Okay, so that was Voyager 1, and there was a similar jump with Voyager 2. So anyway, this convinced people that the heliopause was really crossed. So anyway, this is the picture then, a cartoon picture of, here we have the boundary between the solar wind and the interstellar medium. Here's the direction of Voyager 1 and Voyager 2. And they sampled some of the detailed structure in this boundary. So the real boundary is not as smooth as in this cartoon, of course. But, and anyway, the Voyager team or teams they spent the last almost 50 years analyzing the data all the way from launch to the current time. And so they go into either exquisite or tortuous detail, depending on how you view it. Anyway, so that's the picture we have. And okay, so now, so once the Voyagers left the solar system, the mission was redefined as the interstellar mission, which is what I like, the kind of thing I like. So there were some interesting things that happened. So here is showing a spectrum. So this is frequency in kilohertz. So if these were sound waves, would they be in the audio band or not? What do you think? Yeah, it'd be in the audio band. Okay, well, these aren't sound waves, they are plasma waves. So this is a spectrum. This is basically showing how strong the plasma waves are versus year, starting from mid-2012 up to about 2020. It's a little hard to see much here, except for these really bright patches here. So those are called plasma oscillation events, and they're quite interesting. And I should say that these were known well before we got involved with the project. So, so what are they? Well, when there's a big flare on the sun, it's really called a coronal mass ejection. There's a big shock wave that propagates out, and it actually penetrates through the heliopause, and it shakes up the interstellar medium and produces these bright patches here. There's a direct relationship between frequency and the electron density. So again, the electron density, something like 0.1 electrons per cubic centimeter, quite small. But anyway, like I say, there's a direct relationship between this frequency and the density here. So anyway, you can see that as time goes on, there's an upwards going trend of the density like so. So anyway, that's that. Oh yeah, and so then, so what people have done is, again, I emphasize that these are not sound waves, right? They're plasma waves. Nonetheless, people have converted them to sound, and hopefully this will play. It's a little weird, I have to say. It is what it is. You can find those in all kinds. Okay, so I need to advance here. That was not part of my plan here. It's also not my computer, so. Okay, let's get past this slide. Ben, I think it's stuck. Yeah. Yes, yeah, that's good. Okay, so anyway, so in 2019, we submitted a proposal to NASA because they had a call for proposals to analyze data in the interstellar mission. And so we had this idea that, so the Voyager teams had already found these kind of events. What our thinking was that there should be plasma oscillations all the time, maybe just weaker than usual, or weaker than these. And so we wanted to dig into the data and use our own algorithms and software and so forth. So we put in a proposal in 2019. It was accepted. It funded Stella for 3 years. And so she wrote code. We developed the algorithm, and by, shockingly, we did find what we thought we could find, much to the surprise of the Voyager team, I should say. So anyway, what's shown in the bottom frame here is essentially the same frame here, but now with a stretch of the color-coded spectrum, such that these patches are sort of burned out, so that you can see this very faint line here. And that's the sort of ordinary plasma oscillations that we were looking for. So, you may say, well, big deal, what, so what? Well, anyway, there are lots of connections to other astronomical measurements, and that's what I hope to get across. So you can see that it is faint, but it's also persistent. There are these dropouts. That's when the telemetry was failing. So keep in mind that as the spacecraft gets further away, the signal gets dimmer and dimmer. Also, the power supply is waning. It takes a bigger and bigger antenna to detect the signal as Voyager propagates out. And so there's a limited number of big antennas on the planet that can do that, that can handle the telemetry. The other thing I wanted to say is about the bit rate. In other words, how fast is digital data sent? Does anybody, I bet there's some people here that remember, or at least have seen in movies or whatever, the 1970s modems that we would use at home, where you take a telephone handset and cram it into this device, and you might get something like, if you had an expensive version of that, you might get 2 kilobits, 2,000 bits per second. The Voyager spacecraft is less than that in terms of sending data back. So it is really quite slow, but there's no other spacecraft out there that can send data like what we have analyzed. Okay, so anyway, I'll try to get across why this is interesting. A lot of people thought it was interesting, but anyway, here's a schematic view of the same thing that just traces out this signal. You can see it's wavering around, and that's the interesting part of it, is it's wavering around. Yeah, there are other things you had to work around, like the power supply generates a spectral line at 2.4 kilohertz. That's sort of local interference on the spacecraft that you have to work around, and that kind of thing. And then here's the relationship between the frequency omega and the electron density. So this is just very simple plasma physics. Just take my word for it. Okay, so anyway, this got a lot of press. So it was published in Nature Astronomy, and it was on the cover here. So this is a picture of the interstellar medium with supernova remnants and things in the background, and there's the little spacecraft. So anyway, this got a lot of press, actually, and so you can see there's just 3 examples here. So people picked up on the idea that this was a persistent hum, coming from the interstellar medium. So persistent hum, or in this case, eerie hum, or ominous hum. So take your pick as to what you like. Either way, it captured a lot of interest. Okay, and then, so now let's look more quantitatively, like why were we really interested in this scientifically? So here is the persistent hum, or I'd call it the plasma spectral line, versus frequency and time. So we started detecting it quite easily in data from 2017. We started looking at the data in, I guess it was early 2020. But anyway, it's this variation here that's of interest to us. because, as it says at the top, these are density fluctuations that trace interstellar turbulence. So turbulence is something that affects us in our daily lives. Get on an airplane, you don't want to have much turbulence, for example, but also, in a number of applications, turbulence enters in. So we want to analyze this not just as a picture of this varying thing, but in terms of a quantity that we can relate physically to what's going on in the interstellar medium. So we use something called the power spectrum. It's a wave number spectrum, and this is the expression of that. So Q is wave number, and we have a power law, meaning that we think that the power in this line is, or in the fluctuations here, are described by wave number to the minus beta power. Okay, so you may not know what a wave number spectrum is, but it basically, all it's saying is how much amplitude, how much variation is in slowly varying things here compared to rapidly varying things here. And the answer is we see both of those, rapidly varying, slowly varying, and everything in between. And this is the quantitative way that we describe such things. Okay, so I also wanted to add that, after we published our paper, more data came in, and there was this, you can barely see it, but there was another jump in density here. So you can see the faint line there. Then there was a telemetry gap, and then a rise here. And it's a rise of about 15% in the frequency. So that's of interest to us. That could be another effect of something happening in the sun, some solar activity. But the thing is, it doesn't correlate with any solar activity that was being monitored on the sun. So I think most people in the business would say, okay, this is probably something that related to the sun, but we don't quite understand it. We like the idea that maybe this is an event that came from somewhere else, like a different star, for example, because other stars will have their coronal mass ejections and send shock waves towards us. And so we kind of like that idea. It's very speculative, and there may be no way of really proving it or demonstrating it, but that's the kind of thing we're interested in. Because a lot of astronomy these days has to do with things that go bump in the night, as it were, transients, explosive events. People are really big on explosions and shock waves. So that just is that. So now I want to connect this to the broader interstellar medium. So the interstellar so this is a cartoon picture of our galaxy. It's a spiral galaxy. The sun is about here. It's a barred spiral. It's got these spiral arms. And as it says here, about half of the mass of the galaxy, and I should be technical, half of the baryonic mass is in the interstellar medium. It's in the gas and dust between the stars. It's not all in the stars. And anyway, like it says here, the ISM, as I'll start calling it, it regulates star formation and influences planetary habitability. So it's of interest for people that are looking at planets in other planetary systems and what their environments may be like. Okay, so we spent, so my group has spent a lot of time over the years studying the broader interstellar medium, and it's using objects called pulsars for the most part, not exclusively. But the thing is, the Voyager data fill in, as it says here, a critical blind spot. And in fact, it's called, there's a technical acronym now, it's called the VLISM, the Very Local ISM, as distinct from the local ISM and the general ISM. So let me explain that, because the Voyager team uses VLISM as a technical term. What that means is it's the part of the interstellar medium that's still affected by solar activity. If you go far enough out, the sun's gonna, its events will just be too wimpy to do anything. Okay, so anyway, here's an example of a simulation of turbulence. So I grabbed this off of MIT website. people are very interested in turbulence in the galaxy for a lot of reasons. The one I put up here is that this turbulence is driven by supernovae. So supernovae do a lot for us and to us. So when a star explodes, it spews out all of the elements that have been formed in that star. And so we are made of, I think you all know this story probably, that we're made of elements that were spewed out in supernovae. So that's one thing, but the supernovae also generate cosmic rays, and those cosmic rays propagate through the galaxy in an irregular way. They're not moving on ballistic paths. They're moving on random walks, and they're random walking through turbulence like this. So even though this looks like it's a fairly simple kind of motion, it's extremely difficult to do these kinds of simulations in 3D, especially when you include a magnetic field. And you have to include a magnetic field because the galaxy itself is magnetized. So there are magnetic fields that thread through the galaxy and influence things. Okay, so now I want to, it's cut off at the top, but what I want to now do is link this up to pulsars that we use for probing the interstellar medium in yet different ways. So a pulsar is a rotating neutron star. So here's a nice animation of that. What the caption says here is that pulsars are, I think I said something like ideal probes of interstellar plasma. Okay, so anyway, a pulsar is a neutron star. A neutron star is exotic. It's left over from some kinds of supernova explosions, about the size of Ithaca, but with more mass than the sun has. And so in this, so some of them are spinning once per second. The fastest ones are spinning about 600 times per second. So they're really quite weird. But anyway, the reason they're called pulsars is because they have a magnetic field that's on a, that has a magnetic axis that's typically skewed from the spin axis, just like in the animation. And there's radio emission along the magnetic poles. So this acts much like a lighthouse. So the lighthouse beam goes around, and when it points at you, you see a blip. All right, so you can look at the details of each trace here. Each trace I'm showing here is just one sweep of the pulsar across our line of sight. The important thing for this talk, however, is how we can use these to probe the interstellar medium. So that's what's shown here on the right is, it says dispersion delay. So this is showing frequency, so radio frequency. So this is not quite, you know, it's well above the FM band, if you know where the FM band is. Your 2 gigahertz router for your Wi-Fi would be at a frequency that's somewhat above this plot. So this is not too far away from your Wi-Fi frequency, but it's a wide range of frequencies. And so what happens is that you can see that the pulse arrives, so this is time, and the total time here is maybe about 100 milliseconds, so a tenth of a second. You can see that at high frequencies, the pulse arrives earlier than the low frequencies. And we understand this completely. Again, it has to do with the ionized gas. And so the arrival time scales like this, 1 over frequency squared, and it involves this quantity called the dispersion measure. That's the integral along the line of sight from us to the pulsar of the electron density. So the same quantity that Voyager is measuring. Voyager is measuring that electron density directly. With pulsars, we're condemned to measuring this integral, and then it's our job to unravel that integral. So we have measurements of this dispersion measure for thousands of pulsars, so thousands of lines of sight through the Milky Way. Okay, so now what is it? Okay, it restarted the, I think it doesn't like the animations. pulsar. It spins once every 89 seconds. Tested it earlier. You can play this as a sound also. Sound didn't work earlier, so. Okay, so the important thing then for trying to connect this to Voyager is that we have measurements of a number of pulsars. So we have another spoke diagram, kind of like the one that was on the gold record. Here now we're showing the directions to pulsars and their distances as measured precisely. And then what we determine is what the electron density is along the line of sight, the mean value. So we have measurements for a number of pulsars, and the electron density varies a lot, and it varies a lot because of the turbulence in the interstellar medium, plus other structures that are there. So what I'm showing in this figure is a scale that's much bigger than the very local ISM that Voyager is probing. So this is, that's 1,000 parsecs. So that's going from the middle here to there is about 3,000 light years. That's still our local region of the Milky Way. Milky Way is much bigger than this. And then these sort of greenish blobby things here represent structures, clouds that have been identified in the local ISM from a whole host of astronomical measurements, looking at stars optically, looking at the spectra from the stellar atmospheres and that kind of thing. And anyway, this is of interest because we also know that the sun is moving through different clouds over long periods of time. And the point is that the heliopause where it is today is determined by the kind of structure that the solar system is sitting in today. If you go back far enough, we might have been in a much denser cloud and the heliopause would have been much closer in. And then later on, it may be in a much thinner gas part of the Milky Way, and then the heliopause would move out. So you can also entertain the idea that there may have been episodes where the biosphere was affected by the relatively local environment that the solar system was moving through. The extreme version of that is if a supernova explosion went off relatively close to the solar system, then the heliopause could actually have come in to where the Earth is. And who knows what might have happened at that point. So there's no example, there's no data in existence that indicates that that has happened. But there have been a number of catastrophes in the biosphere, like from impacts and things. But people do talk about the supernova possibility. Okay, I wanted to give you another example of pulsar data. So this is showing 15 years worth of data of monitoring a single pulsar with these, this phone number as we call it. And this is a millisecond pulsar, and that particular one spins about 600 times per second. These really rapid rotators tend to be the most stable in their rotation, so they act like, we use them as clocks, very precise clocks. And this object and a few dozen of others are used by the Nanograv project, which we're involved with. And we recently announced the detection of gravitational waves using millisecond pulsars as clocks. So that's another story in itself. But for now, what I want to highlight is this top frame here. So this is showing the variation in dispersion measure over these 15 years. So that's a variation in what we call the column density of interstellar electrons. And you can see it has this statistical behavior, this unsteady behavior, and it actually turns out to be due to the same or similar turbulence as what affects the Voyager data. And that's the link. As this is on a much longer path length. This is more, for this particular object, it goes out about 5,000 light years, whereas Voyager is some tiny, tiny fraction of a light year, the measurements. But nonetheless, there's commonality between these data and the Voyager data. Okay, so we try to, we're in the process of putting this all together in terms of this power spectrum that I mentioned before. And I'm just giving 3 examples here of data that we're using. So again, the power spectrum just tells you how strong the variations are on different length scales, if you want to view it that way. So anyway, the first of well, let me start here. So this is the dispersion measure variation from one of those millisecond pulsars that I talked about. So again, something like 15 years of data here in this, so we like to characterize this in some statistical way. Here's one example of a spectrum on a given day from the plasma wave system on Voyager 1. You don't see much here. This is the power line interference that I mentioned. I think on this particular day that the weak hum was not particularly visible, but nonetheless, that's the kind of data that we can use. So let's see, C maps to this part of the spectrum, B maps close by. But then another very interesting kind of data that we look at are these bow shocks produced by rapidly moving neutron stars moving through the Milky Way. So what does that actually mean? What's a bow shock? Take a boat on a lake, plowing over the surface, it leaves behind a bow wave. Same idea, except now it's in 3D. You're plowing through the interstellar gas. This particular object is interesting because it's moving. This is a neutron star that's moving about 1,000 kilometers per second through the Milky Way. Let's compare that to how fast we are orbiting the sun. Does anybody want to yell out the number? I know some of you know it. It's 30 kilometers per second. We're moving at 30. So this is moving 1,000. So it's supersonic. It's sort of like Mach 100, if you can think about that. So it leaves behind this bow shock, and we use the contours of this bow shock to also constrain what the power spectrum looks like. This is depicting that. So what I was showing you in that previous slide was just the tip here. So the neutron star is right at the tip and it's moving in that direction. We've measured the direction of motion. And then the fainter body here, as you can see, this explains why we call it the Guitar Nebula. And then other stars, ordinary stars, also plow through the interstellar medium and leave behind these bow shocks or produce these bow shocks. Okay, so I just want to say a bit more about the Guitar Nebula. So we discovered it in 1992, and then in 1994 with the Hubble Space Telescope, we made this image, and then another one in 2001, and another in 2006. So if anybody argues against professors having tenure, I would say it's so that you can do long-term projects like this. Okay, so anyway, there were these 3 measurements that we did. Then another group 4 years ago made this image with the Hubble Space Telescope. So the X here represents the position of the tip in 2020. And you can see that if you go back in time that, that's not where the tip was then, but it's progressively moving in this direction. So we're just at, it's almost like a 4-frame movie of the motion. Not impressive as a movie, but it's impressive as an astronomical result. Okay, so anyway, we have studied these contours, and again, it's a laborious thing, but we infer a lot about the surrounding medium because it's the surrounding medium that changes the shape of that moving bow shock. Okay, so so we and others have been pushing this theme of linking up astronomical measurements, with telescopes and things, remote sensing, with the in situ measurements that Voyager has done. And so Stella led the writing of this white paper for this year. It's called Heliosphere Meets Interstellar Medium in a Galactic Context. So it's putting everything together. But this is a planning document for future things. Okay, so yeah, so here's another depiction of our locality in the galaxy. So the scale here is between tick marks is about 10 light years. There are these various local clouds that have been identified. So this isn't just some random sketch. This is based on data taken over many years to describe what our locality looks like. So anyway, it goes back to what I was saying earlier about the sun moving through this structure and the heliosphere being affected by that structure. Yeah, so the sun will leave one cloud and enter another in about 2,000 years. Conditions within our solar bubble will be very different when we enter a new interstellar cloud. Okay, so going forward, like for that white paper, there are a number of questions that come up. One is, how far out does the sun exert influence on our interstellar backyard? In other words, where does the very local ISM become just the local ISM? That's an interesting question because the sun has lots of sometimes violent activity that affects the surroundings. Other stars as well. So at some point, we will see events coming from other stars. They're of interest, if you're interested in the properties and turbulence of interstellar plasma. But it's also of interest ultimately to astrobiology and habitats. Let's see, how unusual or typical is our interstellar backyard compared to the rest of the galaxy? My take, I would answer this question already as I think it's pretty typical, but it's the details that do matter. I would also say, though, that and there may be a reason why the sun is in, and we are in our location in the galaxy, because if you go towards the inner galaxy, there's much more violent behavior there. The supernova rate is higher. There are dangerous objects called magnetars that spit out lots of powerful things that are not so good for habitats. What will happen when the sun enters a new interstellar cloud? Does the heliosphere have a bow shock? That's more of a technical question that people in the business are concerned about. It all boils down to how fast is the sun and the solar system moving through the interstellar gas. So I mentioned that Guitar Nebula pulsar is Mach 100. We are sort of Mach 1. So we're on the borderline of there being a bow shock. So people would like to know if there is a bow shock for fairly technical reasons. Okay, so that's part of it. But there is some bad news about Voyager 1. So this was an email sent just a week ago by Linda Spilker from JPL. Dear Voyager colleagues, here is a brief update on the Voyager 1 anomaly that occurred on November 14th. Voyager 1 is communicating with the Deep Space Network, but the telemetry is still not usable. So far, the Tiger team efforts have been unable to fix the problem. They continue to study the problem and to try different solutions. So this is a little bit difficult because you send out a command from the Deep Space Network. It takes almost 24 hours for it to get to the spacecraft. Then you wait another 24 hours to get some kind of response. So very slow. There is you can search for this web page about, humanity's most distant space probe jeopardized by computer glitch. Anyway, there's going to be an update at the Voyager team meeting in March. So it could be that this is it for Voyager 1. Voyager 2 is still sending some data back, but it's not the same instruments. So for us, the data aren't quite as interesting. So the last thing, I think this is the last slide I have. So looking forward, so there is discussion. Well, I guess it says here, Voyager 1 and 2, they've started to, even without the glitch, they've started to power down some of the instruments because of the waning power supply. But the power supplies, people estimate that they might completely go in around 2025. If we're lucky, they might go till 2030, but that's it. But meanwhile, people have been talking about another mission, which is called the Interstellar Probe. The idea here would be to explicitly send out a mission for studying the interstellar medium, and it would be launched and boosted in such a way that it would go like a bat out of hell to the interstellar medium, meaning about twice as fast as the Voyager spacecraft. So I got this slide from Stella, and I really kind of laughed when I saw this statement. A new interstellar probe mission could take us twice as far as Voyager 1 did in just 50 years. And I said, well, for me, 50 years sounds like a long time, but she's young, so maybe she'll see the benefits of this. So thank you. Are there questions? Are you?
There we go. All right, so thank you again. So now we're gonna open the floor to a Q&A. Ask anything you like, just put your hand up and I'll come over with the mic. Let's start right here.
Thank you. Thank you for speaking to us today. 2,000 years from now, leaving the current interstellar cloud, seems like, I mean, it's long for us, but it's not so long in the grand scheme of things. I'm wondering if, like maybe in the fossil record or is there other historical data that suggests when we might have entered this interstellar cloud, and has it resulted in any changes in earthly conditions?
For a cloud, no, but there is evidence that supernovae have gone off, not super close to us, but close enough so that some of the radioactive elements have been found in deposits and sediments. And so people have estimated, like, okay, when did that happen? Because the decay, the half-lives of the isotopes. So there is some evidence along those lines. The other thing I'll say is that before people, it's been about, well, 40 plus years since I'd say people came to an understanding of what the dinosaur extinction event was. It was an impact. But before then, people talked a lot about supernova explosions and volcanic activity and things like that. Yeah.
Thank you so much. I was wondering if on the image you showed with the very sudden change in the hum, it lined up perfectly with when the device was out. Have people?
Oh, so in 2020 when there was that.
Yeah,
Yeah.
yeah.
It
Have
was
people wondered if the device was impacted by that type of shift, and that's why it struggled?
People worry about that all the time, but it was far enough, or there was enough time after that dropout that you saw the baseline and then the jump, so it wasn't really simultaneous with that. But yeah, that's a good question, and you have to wonder, this stuff is 50 plus years old. If you consider when it was designed, it's amazing that any of it's still working.
Thank you for the talk. So I had like a two-parter question.
Sure.
At the very first, like when you first started, you showed a diagram that showed both of the Voyagers going off in different directions at the
Right.
ecliptic. So the first part of my question is there anything like majorly different that each of the Voyagers have found going in opposite directions? And then secondly, like, do you have a favorite Voyager? Do you prefer one over the other?
Yeah, I'll answer the second. I prefer Voyager 1 because it has the plasma wave subsystem that we've made use of. As far as whether, they've discovered different things or detected different things, largely no. But the details are different. So like when Voyager 2 crossed the heliopause, that structure that I showed you for Voyager 1, it didn't look quite the same, but there was still a fairly abrupt change. But there was a lot of bumps and wiggles that are due to real things that were different in detail, like I say, but not in some qualitative sense. But it's also true that Voyager 1 did not do a flyby past Uranus or Neptune. So Voyager 2 got to claim that.
Thank you again for your talk. So personally, when I hear interstellar probe, I think about breakthrough starshot and light sails and that sort of thing.
Yes, yes.
Yeah. So Is there any thoughts about that in terms of interstellar medium instruments, or would the instruments have to be so big that you wouldn't be able to fit it on something that's that small and going that
Yeah,
fast?
that's a very interesting question. I think you kind of answered it. Yeah, instruments need to be big. You need long antennas, long wires. So the Starshot, so I'm involved with one of the breakthrough projects. It's the SETI project, Breakthrough Listen. And I will say that there is so SETI is a search for extraterrestrial intelligence. People have used radio telescopes to search for signals from nearby planets and looking at exoplanetary systems and so forth. But one interesting connection here is that those projects use the Voyager spacecraft as a test signal because it's weak and you have to detect it in a lot of noise. But for Starshot, the idea is that you have a really tiny payload, like the size of a computer chip that would have a little camera on it. And then you'd have a sail, very thin membrane-like thing. And the idea is to launch these things to get them up to a reasonable fraction of the speed of light. And so the way to do that is to blast these thin sheets with lasers. And it's a tall order. So people are experimenting with lasers and things. And Yuri Milner is investing $100 million into that study. But I think it's going to, for me, I think those kinds of things seem very fragile. I don't think they would have enough. So it's really kind of interesting. The idea is to launch them towards Proxima Centauri, the nearest star, and just do a flyby and snap a picture and somehow send it back. But the idea is also to send a swarm of these things, so like thousands of them. So it's very sci-fi, but someone's got to try it.
I will ask a quick question too, if you'll have me.
You said
I'll check some. So when we do move into another interstellar cloud, right, do you have any predictions for what might happen to the biosphere and what kind of climate changes or other things we might experience on Earth?
it would have to be pretty severe, a pretty severely different density. But there are subtle things that can happen, like the cosmic ray rate reaching the Earth could be higher. And you have to worry about cosmic ray exposure. So like airline pilots, for example, that fly thousands of hours over, some period of time, they get exposure to cosmic rays. So it may not be some big dramatic type thing, but more subtle things like that, as I'd expect.
All right, we'll just check Zoom really quickly to see if we have any Q&A things. Which we don't. Unfortunate. Well, just to give a quick closing remark, thank you again, Professor.
Sure.
So in case we have any new faces here, which I do see a few in the back, this lecture series is run by the Cornell Astronomical Society. We're an undergraduate organization here on the campus. We run the Fuertes Observatory across the street that a ways, open every Friday, 8 p.m. to midnight. And we're open to the public, open to anyone who's interested, anyone who's not interested. So please come on by, say hi, don't say hi, do whatever you like, but we'd be happy to have you. So thank you everyone for being here. We appreciate it.